It's my great pleasure today to introduce Dr. Marc Fisher. He's a staff scientist in atmospheric science at Lawrence Berkeley National Lab. He works in two groups there, the Sustainable Energy Systems Group and the Environmental Energy Technology Group. He has his BS, his Bachelor of Science in Physics from MIT. He got his master's degree at University of Illinois, Urbana-Champaign, and then came out to Berkeley for his PhD, all of which were in physics. His research focuses on quantifying and mitigating the environmental impact of greenhouse gas production and human habitation. And his work also includes development of system solutions, so looking at solutions to reduce human impact on the environment with a special focus on greenhouse gases and carbon emissions. So I think a very timely talk and one that I've been looking forward to all semester. Let's welcome Dr. Marc Fisher.
Scott, thank you very much for inviting me, and thank you all for coming. I'm going to tell you today a little bit about, and this is really aimed at the students in the audience, how a physics education enables you to go out into the world, learn about the natural environment, and then do something that both will make your heart full and your mind active in making the world a more livable place. So I'm delighted that people are interested, and I'd like to convey my sense of excitement about this. The overview of the talk is first a few words about the Earth's energy balance. There's a typo. And then a little bit more about what we're doing in something called the California Greenhouse Gas Emission Measurement Project. And in particular, how we're using a combination of what I'll tell you about as inventories from the bottom up. That's essentially accounting as much as we can for all the different sources that might be emitting greenhouse gases, and then comparing those with measurements from the atmosphere that we will use to infer what the sum of all of those small parts add up to, and in particular, whether we made a good guess the first time of what's there. And then sort of stepping back a little bit, I'll show you some fun things that we're doing building instruments to look at emissions at small scales rather than a region of California, an individual facility of some sort, and I'll mention some of those later. First, I want to acknowledge an enormous and essential cast of collaborators and team members. This includes my group at UC Berkeley, at LBL, the Air Resources Board, Caltech, the NOAA Global Monitoring Division in Boulder, UC Davis, UC Berkeley, UC San Diego. Picaro is an instrument manufacturer that's central to some of our work. The Energy Commission is our primary sponsor for much of this, and then another company called Earth Networks that many of you might know of as WeatherBug when you want to know what the weather is somewhere else. So, Earth's energy balance. Let me just ask, how many people have already looked at the Intergovernmental Panel on Climate Change, IPCC? A few. Great. For those of you who haven't looked at it before, I want to go through a quick story about how we understand the temperature of the Earth. And for the physicists among us, this should be something that you can grasp right away in terms of when I have an object and it has some thermal mass and I add heat to it, it's going to get warmer. If it gets warm enough, it'll start to radiate in the infrared with a spectrum of electromagnetic radiation that's characteristic of its temperature. once it gets to a point where the thermal radiation emitted by it is equal to whatever incident radiation it's absorbing, it'll be in what's called thermal equilibrium, and it will reach a temperature that brings it to thermal equilibrium. Does anyone have any questions about that? Because I want that to be something that everybody gets, the idea that energy will come, if energy is applied to something in the form of sunlight or other form of heat, it'll get hotter and hotter until it finds a way to essentially dispel that energy off to the rest of the universe. And what's going on our planet is an incredibly beautiful and delicate dance between sunlight coming to the Earth and being absorbed and thermal radiation being emitted. And let me walk you through this picture. And if you have questions, you should raise your hands. I don't have a huge number of slides today, so I want people to really get this, because this is what I would call fundamental empowerment. If you understand this picture, you understand a great deal. The big driver of the temperature of the Earth is incoming solar radiation. And that's just the fact that we live in this lovely place that's close enough to a relatively stable sun that we get a very constant amount of very bright, wonderful electromagnetic radiation bathing the Earth. Some part of that radiation transmits all the way through the atmosphere and is absorbed by the surface. Some of it makes it through the atmosphere and is reflected back to space. Some of it's actually reflected by the atmosphere back to space. So you see there's lots of pathways for that solar radiation. But the thing that we care about is this net amount absorbed here in terms of the solar radiation. Questions? No? Okay. How do we get rid of that heat, that sunlight that's absorbed? The Earth gets warmer. If we were far from the sun, like Pluto, actually Pluto doesn't exist, I guess, but far from the sun, it would be a very cold and miserable existence. We warm up the Earth until the outgoing radiation in what we call thermal long wave essentially balances what's coming in minus the part that's reflected back to space. Does that make sense? It's an energy balance. And the temperature of the Earth depends on not only how much is coming through and is absorbed, but also what the atmosphere is doing. And this complicated picture here is meant to depict the fact that the Earth is emitting thermal radiation. How many of you know about the Stefan Boltzmann law? Sigma T to the fourth. Good. A bunch of you do. So this stuff here is sigma T to the fourth, where T is the temperature of the Earth in Kelvin, heading back out. Some part of that makes it all the way back to space, but some part of it is absorbed in this sort of intervening layer of greenhouse gases and water vapor. Water vapor is pretty much the strongest, if you want to say, overall greenhouse gas. It's probably water vapor. And because of this greenhouse gas blanket, which is effectively keeping us warm and cozy relative to what we would be experiencing without an atmosphere, a fair amount of that radiation that's emitted back gets transferred back in a loop. And so if you look at this number, 350, and you look at this number, 324, there's only a difference of about 40, if I'm reading this right. I must not be able to read this right, because those don't seem to add up quite right. And there's about 40 watts per meter squared that actually makes it out from the surface of the Earth. This stuff here is the radiation that's being emitted by that layer of greenhouse gas and water vapor. Okay? So you've got many components in this problem, and that's one of the things that makes it very hard not only to sort of grok it from a very quick look, but also incredibly difficult to actually do a detailed numerical simulation of where we are headed in the future. Now, in addition to that, there's latent heat. How many people know what latent heat is? Good. Latent heat is evaporative heat. That is, some amount of this absorbed radiation is going into vaporizing water vapor and making the water vapor that's in the atmosphere then turns into clouds and rains back to the Earth, giving us a water cycle. And I know a bunch of you are thinking about water cycles, so that's important. And then there's another source of convective transfer of heat to the atmosphere. So these are adding heat to the atmosphere. There's some sunlight adding to the atmosphere. This overall energy budget is what we're centrally involved in trying to understand from a climate change perspective, because as you change the greenhouse gas blanket here, you change water vapor, you change clouds, you change reflectance, you change all of these different things. So, if that was interesting to you, read the Intergovernmental Panel on Climate Change report. It's hundreds of scientists who are essentially largely doing it as part of their academic activity to bring together as much solidly peer-reviewed information as possible to tell you a complete story, as to the extent that's currently possible, about how the Earth is behaving and where we're headed. So now I'm going to sort of narrow down onto one little teeny part of this overall Earth science problem, and it's anthropogenic, that is human-caused forcing from pre-industrial, that is before there were enough people messing with the planet that it really made a big difference. Although you go back in prehistoric times and there were people burning to change where animals moved, and we'll see in a minute that some of that could have effects. This is the change from sort of before major changes to the present when we have plenty of major changes. And what I want you to look at here is these bars. And so this first one here says CO2, and it says radiative forcing by emissions and drivers. And this bar here says 1.68, and none of you can see that way in the back, but I'll just read them to you. 1.68, and that's watts per meter squared. If we go back, look at the number for how much is coming in, 342. Look what's going, and look at the sum of what's going out. They're nearly exactly in balance. There's actually a slight imbalance right now that's caused by this radiative forcing, but most of that imbalance is currently being taken up by the biggest heat capacity of the Earth system. And what do you think the biggest heat capacity in the Earth system is? Is it the atmosphere?
The ocean.
The ocean, very good. The ocean is this enormous thermal mass. It's like a billion kilograms or something. I can't remember the number exactly. And it's in good enough thermal contact that a lot of that extra heat is getting pumped into the ocean. And the only reason that we're not cooking right now, relative to where we'd be without the ocean, is it's rescuing us. And so this is a small perturbation, only about 1.5 watts per meter squared. And the reason that's sort of the biggest one on this chart is what? What is causing the change in CO2 in the atmosphere? Burning of fossil fuels. Now, there could be, and I'm going to use the word a little bit pejoratively, a denier who will tell you, oh, no, that CO2, that's really not something caused by humans, but that's something that we can now show is unambiguously a human-caused change in CO2. And the way we do that is by looking at the radiocarbon in the CO2 added to the atmosphere. And if any of you know anything about radiocarbon, it's an isotopic subset of CO2. It has 2 extra neutrons. It's carbon-14 rather than carbon-12. And it only exists on Earth with the residence time of about 5,700 years. And then it does a little nuclear reaction and becomes carbon-12. So if we've got less carbon-14 in the atmosphere over time, it tells us that the addition, or relative to the total CO2, we're doing something that's adding radiocarbon-free CO2, and that's fossil fuels, because fossil fuels have been around since fossils. They don't have any more radiocarbon. Any questions? Let me continue. After CO2, there's methane. And I'm going to spend a long time on methane, so I won't spend much more time now. It's less than CO2, but it's non-trivial. There's something called halocarbons. Those are essentially industrial chemicals that were used to run refrigerators. Yes?
How much carbon-14 is in solution in the ocean?
In total mass? No.
Relative.
You mean relative? I would say that in the surface ocean, the carbon-14 is in probably a small disequilibrium with the atmosphere, and as you go deeper and deeper, you get more and more, you get farther and farther from the current equilibrium in the concentration in the atmosphere. So you get more and more radiocarbon as you go down into the ocean. Although, now you're sort of putting me on the spot. I don't know whether the residence time of the deep ocean is so long that you start to have radioactive decay that depletes it or not. So I can't answer that question really well. I'm embarrassed, but not too. So then after halocarbons, which we'll just call refrigerants, those are the things in your AC on your car. Well, actually, these days they're not, but they were in your refrigerators back when the refrigerators were great clunky things. There's nitrous oxide. Does everybody know what nitrous oxide is? It's what you get from the dentist if you're lucky. There's carbon monoxide, not nice stuff. There's non-methane hydrocarbons. There's NO2, which is essentially a burning product. And then there's aerosols, which look very uncertain. Look at the huge error bar on aerosols. Are aerosols warming the atmosphere or are they cooling it? Well, it's sort of hard to say because it depends on what kind of aerosol. Then there's cloud adjustments due to aerosols. People pretty much think the cloud adjustments are negative. That is, those are on net cooling. And then there's albedo change due to land use. I should say, albedo change is reflectance. So it's how much does the sunlight that hits the Earth get reflected back. And if you change the cover of the Earth, you change the reflectance. If you make ice into soil by melting all the ice, you get less reflectance. If you take a green forest canopy and make it into reflective soil, it might actually get more reflective. And that's what this seems to suggest right now. In sum, and I just want to keep going here, in 2011, it's estimated that there was about 2.3 plus or minus about 1 watt per meter squared of net forcing due to all these different human activities, which seems like a small number, but there's a lovely website where one of the really current premier climate change scientists equates this to every person on Earth boiling 30 kettles of water simultaneously. That's how much heat that is if you put it onto the Earth. It's like every one of you running 30 kettles at once. It's something to think about. So the result of that forcing has been, from 1901 to 2012, warming the Earth. This is a map made from space where people have very carefully calibrated what the Earth looks like, and you can see that in general the Earth is warmed, and there's some places where it's more and some places where it's less. And this is unambiguously due to this gradual, persistent addition of greenhouse gases. So now I'm going to take you on a little bit of a deeper look at where we're headed. This plot shows what the Earth's temperature has looked like in degrees C relative to present. So in the sort of few decades before present, the Earth was actually a little cooler. And for those of you who are already plugged in, does anyone want to raise a hand and suggest why was the Earth cooler in those decades before? All right, nobody said anything, I'm just going to say. It's because we were burning lots of fuels that produced aerosols. It's a little complicated. And the aerosols went up into the atmosphere and they made the atmosphere reflective. You can actually look at what the reflectance of the atmosphere was due to different aerosols, and you can find that this is somewhat explained. Now, I don't know how many of you were paying attention when Mount Pinatubo erupted in 1991. How many of you had your pipes freeze in California? How many of you had ever had your pipes freeze before or since? The Earth system in the atmosphere is tightly coupled. And if we start doing things to the atmosphere, we feel it right away. Now, if we kept burning fossil fuels and doing the other sorts of emission that we're doing at a very, very low level, and I'll explain that in a minute, sort of the best possible scenario that people have been able to run suggests that the Earth is going to warm about 1°C relative to where we are today. And that's looks like a pretty small, and actually this error bar suggests, a somewhat uncertain number. But this is something that people have not even really begun to address at a policy level in order to get us to this point. What this would require is that we stop increasing emissions in 2025, that's in 10 years, and then we turn it off. This is petagrams of carbon emitted to the atmosphere. And we turn it off, slam dunk hard, so that it's down by around 2100. If we burn fossil fuels in a slightly less moderate way, we could expect different scenarios for carbon added and different amounts of CO2 buildup in the atmosphere and different surface temperature changes. And really what I want to get at here is this, what they call RCP 8.5, which means 8.5 watts per meter squared. That would be something that is not even coming close to burning the fossil fuels that are available on Earth. It's actually something that could happen if we don't pay attention. And it will warm the Earth about 4°C after another 1,000 years. And it will melt all of the ice, and it will turn the Earth into something that we really haven't seen since dinosaurs roamed the Earth, if at all. And I'm not enough of a climate scientist to really couch this in a deep way for you, and so I'm doing it in sort of the big picture. We don't want this to happen unless we want to essentially go on an very poorly understood journey into a different Earth. And the principle of caution would suggest, to me at least, that we might want to avoid this. Yes?
Mark, the maximum one that's being presented here, I just want to have this clear.
Yep.
At RCP 8.5, we're just going back to that overall, how much are we heating every square meter of the Earth, like the average of an extra 8.5 watts.
Mm-hmm.
That's a case whereby we wean off in some way. I mean, it actually has weaning in it, and it does not use all of our reserves of carbon-rich fuels.
Not even close.
Okay.
I mean, this red line here shows it grows to about 2150, and then it drops. And they had to make up something, and I did not understand the exact reasons why they chose that particular scenario for emissions over time. You should go and read about it if you're curious. All I wanted to do was to get you thinking about the fact that we live on this sphere, and by adding greenhouse gases, we change the temperature of the sphere in a very simple way from the big picture, which is just that we're essentially putting a blanket on it. And the details of this are hard to work out in exact detail. There's one thing that I should say about particularly these big change scenarios. These big change scenarios assume something which is almost certainly not true, which is that once we get the Earth hot, we really still haven't changed the sort of biogeochemical processes that either take carbon out of the atmosphere to grow plants or release carbon to the atmosphere that has been stored over hundreds of thousands of years in parts of the Earth where there's immense amounts of carbon just locked up, not as fossil fuels, but as essentially soil organic matter. So I do not want to be alarmist, but I think you want to pay attention. So now we're going to completely shift gears from Earth science to what I'm doing today, which is, to be a little bit self-deprecating, an enormous accounting problem. And the reason that it's an accounting problem is that I feel incredibly fortunate and proud, and you should too, to live in a state that has actually started to take greenhouse gas emission control seriously. We're the only place on Earth right now that actually has standing laws that are requiring greenhouse gas emissions reductions. And the Climate Solutions Act, AB 32, which many of you may be familiar with at some level, which says we will just scale back to 1990 levels by 2020, is in place, and there's money being traded in terms of emissions reductions, and this is something that is wonderful. You know, from the perspective of business, and now I'm going to sort of get on a little bit of a soapbox. If we get in front of this, that is, you, physics students, engineering students, go out and make the world a more carbon neutral place by using more renewables and more efficient appliances and better cars that don't burn fuel so much. It's not only going to be something that makes the planet more livable, but it's going to be something that keeps you employed, because everybody else, once they wise up, are going to be wanting to do it, and it's happening here first. It really is. You would not, if you hadn't been looking at this, and I haven't really either. My wife has been doing this for 20 years, and she says, I cannot believe what's happened today. There was a day this summer where 20% of the electricity being used in California was generated by PV. And for some of you may just go, oh yeah, big deal. But for someone who came from there being none, it's incomprehensible how quickly things are changing. And there is money to be made if you go out there and figure out how to do it well. Yeah.
And PV is photovoltaic solar power, I thought.
I'm sorry, I should have said photovoltaic means essentially a solar cell. And for those of you who are semiconductor people, this is where it's at. Going and figuring out how to make multi-layer solar cells is something that, you know, SunPower is a premier institution in the South Bay. I'm not going to go on further because I want to get this talk done before it's night. But the governor, I can't believe the Terminator did this, but he showed immensely good judgment. And he said, we will terminate emissions by 80% below 1990 by 2050. And that is a big challenge. But we're headed that direction. There are plenty of groups that are now figuring out, how do we get there? Fossil fuel CO2 dominates right now. But that's where we got to start. There are other things that are going on that are much more uncertain. And this plot here shows million metric tons of CO2 equivalent. And I haven't told you about what that means just yet, so I'm going to digress a little bit. And here's where we were in 1990. You can see there's sort of a drop here, and then it sort of picks up. And that's the CO2, and then there are these bars, these red bars are methane, and then yellow is nitrous oxide, and then the green is the high GWP. That's the same as essentially the industrial chemicals. These bars here are really uncertain because a lot of them are coming from biological processes. This CO2 is, by comparison, pretty easy to judge, because every time you buy a gallon of gasoline, somebody gets some tax. And so you add up the tax and you know how much fuel, right? Round number. But these things, it's a cow burping or it's a landfill off-gassing. It's really hard to know just how much the cow burped or the landfill gassed. And so what I'm going to now tell you about is this essentially big test tube experiment we've been doing to measure things in the atmosphere. So now I'm going to focus further down onto methane. It's the second largest forcing after CO2. There's been a sharp increase in the 20th century. Da-da-da-da, dun, 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 here we come. There's the year 2000. Look at that. This is from ice cores and other things. And look how it's rocketed upwards. That's because people have changed how they use the land, and they've changed how they do all kinds of different things. And this is not stopping. It's continuing. Now, let me say something about methane in particular. It is a potent, short-lived climate pollutant. So there's two things about methane that you should understand. One, per unit mass, it's much stronger than CO2 in absorbing infrared radiation and therefore acting as a blanket. Fortunately, it's short-lived, and the reason for that is atmospheric chemistry. There are things called OH radicals. That's basically water missing a hydrogen. And when those OH radicals bump into a methane, they eat it up, and they make something else. Okay? So methane, unlike CO2, does not last very long. CO2 could last hundreds of years before it's absorbed in the ocean or more. Methane lasts about 10 years right now. And putting that all together, if you look at what we call the global warming potential of methane, it's about 90 times per unit mass that of CO2. So 1 gram of methane gives you 90 grams or 86 grams of CO2 over 20 years. I didn't put it on the slide, but if you wait 100 years, this number drops from 86 down to about 33. These are the current estimates from the IPCC. So it changes over time, and it's not, so you have to think a little bit about the time scale on which people are reporting. But let me give you a round number here. If you were, oh yeah, gas, right here. This stuff. If I use gas to do something, and I burn it, that's the fun thing to do with it, right? You warm your house, you heat your water, blah, blah, blah. Maybe you run your car sometime in the future. If you leak 3% of all the gas you burn, that 3% you leak has just as much climate forcing activity in the first 20 years as the remaining 97% of it that goes to CO2. It's pretty rippingly strong stuff, so you do not want to leak it. Now, the methane budget for California is uncertain. And what we've gone and done is try to make it less uncertain, more certain. So here, we're going to go through the litany of what emits methane in California from what we would call the bottom up. There's first enteric livestock. And what that means essentially is that cows have guts that digest cellulose, and they make all kinds of magnificent things in that first stomach, essentially lipids and other readily digestible compounds that then their subsequent stomachs digest in the same way that our stomach digests readily digestible things. We just evolved not to have that first stomach. But that first stomach is also a little anaerobic bioreactor, and it creates methane because it's anaerobic. The carbon that's in there, some amount of it, gets eaten up by microbes, and the cow goes, and out comes a puff of methane. And it's actually kind of fun. If you have a sensitive methane sensor, you can put a cow in a box and you can measure how much methane it produces. Then there's a large amount of methane that's produced from the manure of the cows, and I'm not going to say a lot more about that because I don't really want to talk about manure. Then there are landfills. landfills are a place where we've historically taken lots of carbon, carbonaceous materials, whether it's, I'm just not going to go through the litany of things that we throw in landfills, but that's why we recycle now, in no small part. All that carbon that's gone into those landfills has been essentially entombed in this anaerobic subsurface system, and microbes have gotten in there and they're gobbling up that carbon and making methane as well as CO2. And I don't know how many of you are familiar, in the late 80s, early 90s, we found that California landfills were actually pushing landfill gas out of the landfill because of all that anaerobic decomposition, and the landfill gas was sometimes going into people's houses and poisoning them or making them explosive. Bad thing. So now we largely mitigate landfills, but there's still that methane being produced, and this number is now much smaller than it used to be in terms of emissions, but there's still some. Yes?
Our audience here might drive in the landfills south of Petroleum, right on the way to Nevada, and see the burning of the natural gas at the landfill.
That's right. If you go on 101, there are some stacks, and if you go by, you'll see hot air coming out of this thing, and you're going, why is there a big bad pipe there with hot air coming out of it? It's because they're burning the methane. But I will assure you that they're not getting all of it. They're getting the stuff that's easy to get. And there's a bunch that they're not getting. Then there is oil and gas, and this is a mixture of the places in California like the southern San Joaquin and the LA Basin where we're extracting fuel, and in the process of extracting the fuel, a little bit of methane gets leaked. And I'm not going to say exactly how much because we don't really know that one perfectly yet, but there's another whole part of this that all of you ought to be thinking about if you are living in a home environment. Remember, I opened this thing and let a little bit of gas out into the room here. All of your appliances are letting a little bit of gas out too. And I'll come to this in more detail. This number is one of the ones that I'm spending a lot of time on because we're really not sure how much people are leaking just through their activities. Then there's wastewater. Again, it's the old anaerobic decomposition of carbon thing. Wastewater is full of carbon, and we won't discuss in great detail what kind of carbon, but that carbon is anaerobically decomposed and a certain amount of methane is produced. And then there is rice agriculture, and there it's an anaerobic system with carbon in the soil. So now, here is what we're going to do. We've got all those uncertain sources of methane. What we're going to do is pretend for a minute that we can infer how much is being emitted from the surface by measuring what's in the atmosphere, essentially downwind of the sources, and then say, well, if there's this much entering the atmosphere and we've got this much being measured, the difference of those two tells us about whether the emissions at the surface are right or wrong. I mean, how far off are we? It's called an inverse problem. We measure what's in the atmosphere and we infer what's happening on the surface. Now, how do we do this? It's a bunch of steps, and I'm going to walk you through it quickly. First, we have towers. This is a 2,000-foot tall tower out south of Sacramento, where we climbed up and we put a bunch of sensors on the tower. Well, we don't climb, sorry. I rode an elevator, to tell you the truth. But we then measure what's way up there in the air, and then we do that for lots of towers all over California. So we get essentially a map of how much methane is in the atmosphere above California. We then compare it with how much methane is in air flowing to California. And we don't do the measurements off of California, but our colleagues at NOAA, who are, for all of you, heroes of the environmental movement, the people that are doing the carbon cycle measurements at NOAA are doing something that is incredibly valuable, and they are therefore crucified on a regular basis in terms of their budget. It's really as inexcusable as, well, no, I'm not going to go there. So we have measurements, and then we make a model. of how air moves around California. And this is a meteorological model that we run at my laboratory, which simulates the details of the air motion for every hour of every day, for every 1 kilometer patch of California. And we do this forever, and there's terabytes of unpleasant data to mess with, and I made a little movie here for you to see what it looks like. And what you're seeing here is a mixture of where the wind's pointing, and you really can't see those tiny little arrows from where you're sitting, but these colors are telling you something that is arguably critical for this problem, which is what we call the depth of the boundary layer. And for those of you who don't know what this is, you should take this as a message home with you. The atmosphere is this incredibly thin skin on the Earth, and the very lowest layer of that skin is a thing called the boundary layer, and it's sort of phenomenologically described as the layer of the atmosphere that's in intimate contact with the surface. That is, when something is emitted from the surface, it mixes into that boundary layer, and big eddies carry it along downwind, but it sort of stays in that boundary layer, and it doesn't sort of mix up into the rest of the atmosphere, which we call the troposphere. For example, all the jets fly up high in the troposphere. If you're having a little, squirrely plane, you ride along the boundary layer and you're getting bounced around because of all the thermal motion, and it's miserable. So everybody wants to get out of the boundary layer. But for me, the boundary layer is the place to be because it's where we can actually measure what's going on with the surface. So we have to predict this surface layer well, and I'm going to give you a quick reason why. We emit the gas with some flux rate, that is emission per unit area per unit time into the atmosphere, and it's carried downwind by the velocity of the wind, but it's mixed quickly into this layer, which we'll call planetary boundary layer, PBL. PBL. You'll see this again and again in my talk. The taller the boundary layer, the bigger the volume you're mixing the emissions into. And so the lower the concentration enhancement. Does that make sense to everyone? It's essentially making the box bigger that you're mixing it into. When you have a low boundary layer in the winter, in the morning, have you ever gotten up and you see the fog hanging really low in a valley? That's a really low boundary layer. Have you ever been out to the Great Plains of the United States and seen the clouds, towering above you kilometers up? That's a huge, tall boundary layer. How high the boundary layer is critically important to calculating what we call footprints. And what the footprint does is it tells us, for each of these measurement sites, how much will emissions at different places on the landscape change the signal we measure at the tower. Does that make sense to everyone? Okay. We take this meteorology, we calculate these footprints, I'll show you how. We take a model for where the methane is coming from, we multiply it by the footprints, very literally. We take this map and we multiply it by that map, and then we add up all the pixels for each of these tower sites, and we get what are called predicted signals. We then compare the predicted signals with the measured signals in, fancy word here, Bayesian inversion. What that means is really a very glorified least squares regression. Does everybody know? Has everybody done a fit where you say, here's a bunch of data, and this is the y-axis, and this is the x-axis, and you fit a line to it, y equals a plus bx. Has everyone done that? Okay, that's what we're doing here, but we're doing it with a little bit more sophistication that incorporates uncertainties in as many of these different things as we can capture. And you can imagine there's uncertainty in every one of the things that goes into this comparison between the measured and the predicted. And so we try to capture that. So, going on. Hello? Go on, toots. I'm not going to spend much time on the measurements because I took too long in the beginning. I wanted to give you the big picture. Long and short of it, we build racks full of equipment. And if any of you, how many of you have done the undergraduate physics lab? I see a few hands. Good. Everyone should do the undergraduate physics lab. You just should do it. It's good for you. I found them tremendously fun when I was a student, and I worked in them because I found it so much fun when I was a little older. So we build these racks full of equipment. We don't build everything ourselves. This stuff here are what are called spectrometers for measuring carbon dioxide, methane, nitrous oxide, and carbon monoxide. They're essentially a fancy laser that measures the amount of absorption in a wave band that's specific to the gas of interest, thereby isolating how much of that gas is present. And we have to control the temperature and the pressure really well to say how much is it per unit volume of everything else that's there. It's a nasty mess of what I would call atmospheric chemistry, but we do that. And I'm not going to go through all the details of all the things we measure. By the way, we measure the radiocarbon that I told you about, because we're going to be able to say something about how much radiocarbon is emitted, how much fossil fuel is emitted from California using that. Continuing, we then divide California up into big patches. Nice. And what these are essentially air basins, places where the air is sort of subject to the same general conditions. And we pick these sort of based on the sort of typical meteorology of California, and we then estimate the emissions from these big patches. Now, I'll come back to this in a minute. Here it is. Here's a map, our best estimate right now of where methane is coming from California. And there is a big patch right here in the center, and guess what that is? Yeah, what kind of agriculture? It's the cows. Yes, it's the cows. It's all the milk and cheese. What is it? California, it's the cheese. How many of you love Chloe the cow? I have been going north every so often from Berkeley, and going through Sonoma, it has always been a great joy to read the latest billboard. I will try to recount some of those for you later if you come to dinner and we have some drinks. In addition to that, there are places, for example, the southern San Joaquin, where there's a lot of oil and gas being produced. There's the South Coast Air Basin, where there's lots of people using natural gas for lots of human activity. The San Francisco Bay Area also has that issue. And you guys are right up here, probably. And just human population in our model has a role in emissions, because we assume that if there's people using gas, they're losing some of it. If you ever come to my house, you could almost smell it, because it's an old house and it's got lots of leaky pipes, and I promise I'll fix it. So that's emissions. Any questions? No. I will not spend a long time on this, but I just want to emphasize, we take this kind of seriously, and so we spend years getting graphical user information activity data, and that's basically where are the pipelines. These are all the pipelines carrying gas around California. These are all the oil wells and gas wells all over California. We count every single one that we can get our hands on data for, and we make a map of where we think, this is for petroleum and natural gas, where we think the stuff is coming from and how much. It's what we call an a priori model. It's a guess. And I have to say to you, it's only a guess. We have to give it some uncertainty, and we give it a big uncertainty, typically 50 to 70% in any given patch at a given time, because we really don't know a great deal, or at least we want to be open to the possibility that we don't know a great deal. And then there's dairy. I'm not going to go into a great deal of detail here. I've already told you about dairy. And then we add everything up. And here's the picture for methane. Dairy livestock. There's dairy livestock. There's landfills. There's non-dairy livestock. There's natural gas. There's, I've forgotten what RM is. There's wastewater, wetlands. We even have a little model. Actually, we don't have a model. NASA Ames has a really great group of people that model the terrestrial biosphere, and they have a model for where they think methane is coming from wetlands. And then there's crop agriculture, which equals rice for all of you. Pretty much rice is the only form of crop agriculture that produces much methane in California. And then we can divide that all up by different areas of California. Remember the regions I told you about? and there's a little bit coming from the northern San Joaquin Valley. There's a little bit coming from the southern San Joaquin Valley, the Bay Area, and the LA Basin, and then a few other places. Okay? That's our guess. Now we're going to test it. And the way we do that is by measuring at all of these places that have got red boxes. And so I'll tell you about them. There's Trinidad Head up on the north coast, beautiful place. Tuscan Butte, never been there, but colleagues have. Sutter Butte, some of you may have seen Sutter Butte sticking up out of the landscape. Walnut Grove, that's the tower we instrumented back in 2007, and I'm very pleased with because it's been working for so long. Colleagues have a site in Livermore. We also actually have a site right on top of San Francisco on Sutro Tower. I don't know how many of you are familiar with the Godzilla that sort of overlooks. Many people hate it, but I love it because it gives us data from high up off the Earth. Then Madeira, Tranquility, Arvin, and a bunch of sites, Caltech, a San Bernardino site, Victorville out sort of toward the desert, and Scripps, where it would be fun to visit and go surfing. I'll tell you a tiny bit about this model. It's called the Weather Research Forecast Model, or WRF. And it's written by a group in Colorado at the National Center for Atmospheric Research. It's the model that tells you what the weather is going to be like tomorrow in Sonoma. And the NOAA people have taken this model and they've sort of operationalized it into what gives you what the weather's likely to be like. They can run it forward in time. We don't do that. We run it with essentially as a reanalysis. But we do it with enormous effort. We have 50 vertical layers of the atmosphere. So, from the first, surface to 10 meters to 20 meters, etc. We capture the boundary layer with probably 20 layers, and then we have another 30 that take the rest of the troposphere. Actually, maybe it's even more in the boundary layer. I've forgotten. And we simulate entire California at 4 kilometers, and then the major urban areas at 1. And so I think you're in our grid for 1. We do the boundary conditions from stuff that you probably aren't familiar with, and this is a little more detail than you need. We do nudging of the model, etc. And then we calculate the footprint. And I'm going to spend just a few moments on the footprint. How much time do I have?
7, 8 minutes.
All right. I'm going to just give you a quick sense. How much do we measure at this tower per unit of emission on the landscape? How do we calculate that? What an unpleasant problem. This is effectively, I don't know how many of you have had enough math, it's a Green's function. The thing we get here depends on a different variable, the emission on the surface, and it's essentially, in some sense, a transfer from surface emissions to signal here. The way we calculate it is really simple. We divide the patches of the land up into boxes, and we say at a given time, if a particle released from the tower and then moved backwards through time, we have a time machine in our computer, using the meteorological model, we watch where the air goes. If a particle is over a given patch of landscape at a given time and is within half of the boundary layer depth, we say that's counting toward footprint. And depending upon the amount of time it spends there and the depth of the boundary layer, we give it more footprint weight. So it's a very straightforward numerical approximation. And we do this with thousands of particles for every single hour of every single day for every single tower and estimate these footprints. And here's a picture that shows you particles streaming backwards from Victorville, running past, through a pass in the mountains, and then past Caltech and down south and then out into the ocean. Does that sort of make sense to everybody? The particles, we run the particles back in time. Doing that again and again and again and again, we make up these maps that show us, these are average maps, what is the sensitivity for each of our measurement sites to emissions on the surface of California. And the question is, how good is that model? Well, we got to test how good the model is. There's no substitute for guessing. You've got to go and make a test. And so what we do is we first calculate signals, and then we compare how well we can estimate the signal with how well we can, or how big the difference between the measurement and the predicted signal is. And so here we've taken the emission map, and we've taken the footprints, and we've calculated for each time, and this says 2013 June to sort of August. This is a summer period. We predict the signal. This is at Caltech, and that is the measured signal that we get from the tower. There's the predicted signal plus this background that I've told you about. In other words, the air flowing into California has some methane in it. And then this is the pure background signal. And so these are the elevations above background that are going to be the thing that we use to estimate the local emissions. Okay? We do this for Caltech. We do this for, this is the Walnut Grove Tower, which is, again, south of Sacramento. Notice some of the time the prediction is lower than the measurement. Other times, well, I mean, it'd be kind of hard to find. There are some places where the prediction is a little higher than the measurement. How significant is that difference in quantitative terms? Well, the way we do that is this uncertainty analysis. And this is not the only way one can do this, but it is the way that we have been able to put together essentially a complete picture of all the major sources of uncertainty that we can readily identify. And here I'm coming back to boundary layer depth. We look at the predicted boundary layer depth in our model, and we look at the measured boundary layer depth. And you'd ask, how do you measure the boundary layer depth? We do that with what is called a radar wind profiler. There are instruments that can measure the boundary layer depth, and those are scattered across California. These are the red dots. And we can compare the model with the measurement. And you can see there's scatter about this line, but mercifully, the line is not so different from unity. That one actually does not look so great. Most of the time, the measurement is essentially consistent with the prediction is consistent with the measurement on a statistical basis. But the scatter about the line is non-trivial. And we take that scatter and we run it through that particle model that I told you about to estimate the overall uncertainty due to boundary layer depth in our prediction of the signal. And the long and short of it is that for any given hour of the day, our uncertainty is typically 30 to 60% of the measured signal. It's non-trivial. So we need lots of measurements to average down the noise. So we've done that. We measure every hour of every day, and after a year of data collection, we can start to say something on a statistical basis about the emissions. So let me explain this plot to you. Again, here's the picture that shows the different regions of California, and here are bars that show our guess of the emissions from that prior model that I showed you before. Okay? These red lines are the best estimate of emissions after including this prior knowledge with this model measurement difference weighted by our uncertainties. And for the period from June to August of 2012, we find some regions have more emissions than the prior model, some much more, some only slightly more, some not at all more. And so it depends on what region of California. And we can do that for 2 different years, and we get not totally dissimilar results. And so we start to gain some sort of sense of where are the emissions of methane coming from California. Okay? Questions? Yes?
You don't mention power plants as a source of methane.
No. And the reason I don't is that we believe that once the methane has entered the power plant, it is perfectly combusted. That is, the power plant people want every single joule they can get out of that methane. You may have read the recent paper. No, okay. There was a recent paper that showed from space there was a big plume of methane coming off of the Four Corners power plant in Arizona, New Mexico, can't remember the other states, Utah, Nevada, Colorado, that's right. And what was going on there was not that the power plant is leaking methane, but that there's a huge coal bed that they're pulling coal out of to power the power plant. And in the process of pulling out the coal, and actually arguably that might have been going on for a long time, methane coexisting with the coal was being emitted. Now, my guess is the people digging up the coal probably exacerbated the methane emission, but that's unusual. And so we don't typically associate any methane emission with power plants for electricity. Now, the pipes carrying the gas to the plant and then the emissions in the plant can't be ruled out as zero, but we, at this moment, don't have a model for that we have any really good data for. One idea would be to fly around a power plant, and I'll show you a picture in a moment about that. So, summary. California has been evaluated at sort of this, I would call it the 0th order level for methane emissions using 12 sites. And we're able to constrain most of the regions where methane is occurring. If you sum up all those regions, we get somewhere between 1.4 and 1.5 times what the current California inventory is for methane. That is, we believe methane is being emitted in greater quantity than the state does. And you can imagine that there is some friction generated when you find a result that's not consistent with the bureaucrats. And so we are in a process of refining our estimates. Okay? We need to do this better. Now, attribution to source sectors using additional trace gas species and full annual cycles will improve this estimate. That's what I promise you. And maybe in a year, I will be able to send Scott a paper that shows that that's the case, and we'll be able to tell you a better story. And ideally, we're going to be able to say something about, well, is it the cows? Is it the natural gas? Where, when, how, and how can we make it better? So, just in closing, we weren't satisfied with these towers, so we set out to build instruments, and I love building instruments. So Toby Walpert, an undergraduate at UC Berkeley, came and started working with me, and we took his mom's station wagon and we stuffed a bunch of gas analyzers into it, and we put gas inlets on a sort of extendable pole that they use for putting in front of big moving houses, so that if the person in front runs into a bridge and the pole breaks, they stop the house before it tears down the bridge. Anyway, we also put a very beautiful thing called a sonic anemometer. And really what this is a wind sensor that can measure the velocity of the wind at 10 hertz. Every 10th of a second, it gives you a new reading. So we go driving down the street, we measure the wind, we measure the position of the car as a function of time with the GPS, and we measure how much methane is being observed at each of these 3 heights on the pole. And this is what it looks like when we go past a natural gas pipeline facility in the southern San Joaquin. The 3 different heights are the 3 different colors, and we go past the facility, and kabam, up goes the signal, and then back down. There's something leaking from right there. And because we know the wind speed and we know the distribution of that methane enhancement, we can do what's called essentially a flux integral and add up all of that crosswind motion of methane to tell us just how much is being leaked. So we're building instruments that can in real time quantify emissions. And this makes my heart go thump, 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 that we can do this. Now, that's not enough, because that's kind of a small thing. We want to be able to do this for bigger places like power plants or other. And so we have an airplane, and this is Steve Conley. He's now a research scientist at UC Davis, and he is also an ex-Navy boy and loves to fly airplanes. And so he bought himself a plane, and this is Qianyang Zhao from UC Irvine loading flasks, which we put on the airplane. And Steve actually also has one of those real-time spectrometers that I told you about. And we go and fly around California, and we map out where is there more methane and where is there less. And from that, we can infer the emissions, because we again, knowing the winds, we can do something like what I told you about with the car. Thank you.
All right, let's start with in the front, but Joe, if you wouldn't mind enunciating for the room, because we got a little bit of noise here.
It's interesting, we think of global warming is driven largely by industrialization. And we think of California as a very industrialized part of the world. And yet you're saying that in this state, one of the main global warming gases, methane, is driven largely by cows.
Yes. And I'm going to step back and I'm going to say there is no substitute for fossil fuel emissions reductions. That is, carbon dioxide from combustion is by far and away the largest source. If we go back through the talk to the very beginning, this plot has an offset of 400 million metric tons. If you wanted to take this all the way down to zero, it would be below the level of the floor. So these blue bars are huge. But the reason we do it this way is because I measure methane a lot. I'll tell you about methane. So methane is important because of what I said about it being short-lived. One way of thinking about it is, if we cut methane now, we can actually blunt some part of global warming in the near term and make it a little bit less of a roller coaster ride for ourselves. Now, how easy is that to do? I am not an agricultural specialist, and there are people, and they've told me it is not really easy to produce lots of milk and not have cows burp a lot of methane. So I think milk is great, and so it's not an easy problem. We've got to start with fossil fuels. We've got to drive less, we've got to drive better cars, we've got to not fly as much, telecommute. We've got to figure out how to organize our societies so that we don't rely on fossil fuels so much. And it's actually not nearly as big and bad a problem as you have been led to believe by the fossil fuel industry. Let me answer your question, because you had your...
So if you look at this graph here, then obviously nowadays you have modern technology, sensors, computers, and so on to measure the emission of that methane. How was that done in the past? When you look at the curve from, in the past 1,000 years or so, where does the data come from?
That's a really good question. And it is one of these beautiful stories in science. There are people, actually Scott among them, who go to these ridiculous places like the South Pole. And I don't know, I find it unpleasant. I don't want to go somewhere that cold. But if you go to the South Pole, there are miles of ice that have built up over millions of years. And you can drill into the ice and collect samples of ice from different depths. And from the details of Earth science, which I don't know enough about to really justify completely, you can say, when was this little package of ice laid down in time? And then you can say how much methane is in the air pockets in the bubbles of the ice. It's absolutely incredible.
So your data somehow comes from a different location. If you use all these, the devices up in air, you're not really collecting data from the ice, back
No, absolutely not. I am completely a 21st century person, and so everything we collect is last year or next year. It's not. This is a whole, field of study.
So in other words, we're assuming that the methane emission is globally uniform. If you just cut a small piece of ice, you say, look, this is the level of the methane emission 1,500 years ago. We're going to assume it's basically the same for any other locations.
Well, it's not just a matter of assuming, it's a matter of starting with that as your initial hypothesis and then testing whether there is evidence to support that hypothesis or refute it. And there are detailed studies that have been done on how rapid the mixing of a tracer released into the atmosphere is, and then deposited in the ice. And we have plenty of recent data from the last 50 years at least to be able to say how quickly does something redistribute in the atmosphere. And the time scales for redistribution are sufficiently short that you can date reasonably accurately. And I am embarrassed that I can't tell you for each of these different sites what the uncertainty in date is. But it is small enough that I think that it is sort of the scale of these dots, not, a patch like this. So, I mean, I think this is solid.
Okay, just one more question.
Yeah.
Shut up.
No, it's good questions.
So when you look at the level, we're really talking about ppb level. What sensor do you really use? What's the sensing material to, sensitively measure down to that level, ppb level?
Traditionally, this was done with gas chromatographs. More recently, it's done with these tunable diode laser spectrometers. You can take an infinitesimal amount of air from one of these ice cores and inject it into one of these machines and get a good measurement. It's the way of human ingenuity. They figure out how to do it. And our measurements are comparatively crude. We have, the luxury of sucking in liters per minute and then sipping off of that. But it is possible to use these things for that. And to give you a sense of these instruments, when we measure methane with one of these instruments out of the box from the manufacturer, it comes, and when we apply a known standard that's been supplied by a reference gas laboratory, their analyzers come out of the box good to, in methane, I would say about 2 ppb. It's rare that you get one that's further off. And they've done a really good job calibrating and building it and supplying it. It's not cheap, but it's good. And then this is the amazing thing. It measures to a few tenths of a parts per billion in a few seconds, and it stays stable to a ppb or two over a year without calibration. I mean, it drifts around a little bit, but it's within a few ppb. It's absolutely, and the reason we know this is that we worry about it at a few ppb level, and so we put in a standard some people have dropped off to every day. But we've been doing it, every few hours initially for years, just to make sure the thing really is stable, and they are really works of engineering. So I hope that answers your question.
Thank you.
Please, sir.
Don't plants take CO2 out of the atmosphere?
Absolutely. The plants are an absolutely critical part of the carbon cycle of the Earth. They're taking up the CO2. They're producing organic matter, which when the plant dies, lays down onto the soil. Over some part of that organic matter is then decomposed by microorganisms, making nutrients and essentially recycling that carbon to the atmosphere as CO2. Some part of it is not decomposed, and in certain biogeochemical systems gets what's called sequestered, becomes peat, which might last for thousands of years in soil until you disturb it either with cultivation or with climate change or some other event. So yes, I haven't really talked about the terrestrial carbon cycle in the large, but in the same way that I showed you this picture with these very big flows of heat coming in and big flows of heat going out and the small difference mattering, the amount of carbon dioxide that comes out of the atmosphere into plant material every year and comes back as respiration is absolutely enormous, even compared to the amount of fossil fuel that we're adding to the atmosphere. So you'd say, so what? But the deal is that it's that imbalance that still really matters, because the Earth is, for every bit of its wonder, a very finely tuned system. Yeah, please.
My question is his question too, but where are the carbon dioxide and the methane gas? Is it making a separate layers, or is it almost uniform under the boundary layers?
you could think about the atmosphere as not having, for these very dilute gases, that is, they're very, very dilute relative to the major constituents like oxygen and nitrogen. You can think of them as just essentially diluting into that larger gas, essentially at the rate of whatever the turbulent mixing that carries them away from the source. And so it
doesn't making all layers.
it does not make any layers until you get to the very top of the stratosphere, where the mass effects start to matter a tiny bit, but basically it's uniformly mixed, by the sort of turbulent diffusion and advection of the atmosphere, the greater circulations. Yes.
So somehow we don't have our class that's trying to descend upon this room. I wanted this to continue because this is a really nice discussion. So let's take a couple more questions, but at some point we should adjourn and maybe have a discussion out there. Or if anyone would like to join us for dinner, let me know and we'll do that. But let's take a couple more questions.
So it's kind of stunning to me that you can beat down the error bars that much with what look like 10 or 12 stations. Can you make that intuitive? Is it because you got an inverse problem and you're sampling from all over the place?
It is. We can tell about the emissions, here we go, from these different regions because we have towers in each of those regions, and each of those towers effectively is there all the time sampling the air. And for essentially every day, in the very simplest approximation, every day we have a single measurement. So in a month, we have 30 measurements of what the air is in this region from that tower alone. And if we do this for 3 months, we have on order 100 measurements. If we have 12 towers, we have 1,000 measurements. Each one of these regions where there are major emissions has typically 1 or 2 towers. And so, no, we can't integrate down enormously, but we can integrate down by sort of the square root of the number of data points. And so if we have 100 measurements in a given region, we knock down the noise by about a factor of 10 from the individual measurements. And it is what is called an ill-posed problem in that we only have as much information as the atmospheric motions allow us. And let me go back to this footprint thing. For example, Walnut Grove, which I've spent a lot of time worrying about, that tower, in the summer, the wind comes rushing in the Golden Gate, goes roaring over the delta and out to Walnut Grove. And our footprint is really very much just limited to that particular patch of the landscape. So if there were emissions up here, we would not be able to say much about it from Walnut Grove alone. But when we have enough towers, you can see there is enough yellow here, essentially, enough coverage, just because there are different winds on different days, that we start to get a feeling for it. And, the thing that worries me, and I'm going to be a little bit sanguine here, the thing that worries me is that those estimates of errors that I told you about, remember I said, where was that picture? Here. I said, well, look at this, you don't see much of a bias, right? Well, I'm now worried that we're starting to have enough towers and enough data that we might be integrating down the random noise and hitting some bias floors, some systematic errors in our model. And we can't know about it until we really delve into the sources of bias. And when you start making measurements, you skim the cream, the easy things, and now we're having to go back and look much harder and say, is there something hiding in here? And one of the ways that we're going to do that is by looking over several different years and looking with different combinations of measurements and different models, and as many sort of supporting pieces of measurement information as possible. I just want to be sanguine with you. I don't think that we've necessarily nailed it on the head. I think we're making progress.
But just as a comment, I mean, but that's to the absolute value, or to compare to the policymakers' numbers.
Yes.
Whereas you have this, and you have probably well-trusted differentials from year to year ongoing.
Well, I would like to believe that that's the case. I think it is conceivable that there are systematic biases in one year that might not be present in another. So, I mean, I am being the skeptic here for my own work, and I have to be, because if I'm not, nobody
Someone
else is
will
going to be. Well, nobody else is going to know as much about it, and so this has turned out to be a hard problem because going after those systematic uncertainties is something that we haven't solved yet. So it's a good question. Anything else?
Well, let's thank our speaker.